The city of Kiryat Shmona is the most northern city in Israel. Kiryat Shmona is small and inhabits only about 25,000 residents. The city is surrounded by a few small settlements and agricultural fields. Today, Kiryat Shmona is divided by Road 90, which is the only access to the city. There are future plans to construct a new train station to connect the town to the national transportation network. The suggested location of the new station is outside the city in an agricultural field. What are the reasons to build a transportation hub outside the city? I have conducted a comparison between the location of train stations in Israeli cities to cities of similar size in Europe. As we can see, most of the train stations in Israel are located far from the city center, or even not inside the city at all. Given the planning of the new train station, how might we create a new urban network within the ecological system? And how can we define the right location for urban expansion? The intervention site is 4 square kilometers in area. The site contains the suggested location of the new train station, agricultural fields, streams, and water canals. To find the exact location of the new urban expansion, I have divided the site into 10 meter by 10 meter cells. Each cell will be examined by its physical properties to determine its fitness for construction. Using a series of mapping techniques, the cells are being evaluated for different parameters each time. The first map visualizes the precipitation water flow on the site surface in the form of a heat map. The red cells are very dry and does not experience much water flow. The blue cells are very wet and collect a lot of water. The second map is a vegetation growth map, indicates the growth intensity in the area. The map was created using infrared aerial photos. This map indicates the slope angle of each cell. As you can see, most of the site is quite flat. The next map describes proximity to winter pools. This map created using the water flow heat map. The map shows areas of precipitation catchment and pooling locations. Proximity to streams indicates how close each cell is to a water stream or a wadi. And the final map, the elevation map, indicates the elevation of each cell. As we can see, most of the site is pretty much on the same level. In each analysis, every cell is graded based on its properties. A cell that shows negative properties is granted a low or negative grade. For example, a cell that is located inside a winter pool will receive a negative grade. Cells that show positive qualities will receive a high score. The cell individual grades are normalized and assigned to weights to calculate each cell overall fitness. The weights lower or increase the impact of every trait by multiplying the grade by the weight. The weights are user-defined and reflect the significance of each parameter to the designer. Using the graded cells, an evolutionary algorithm is used to select 1 square kilometer of area from the initial 4 square kilometers. For the selection process, a new parameter is added to evaluate each cell, distance to the train station. The algorithm will move the station and evaluate the result for every new location. The algorithm is instructed to achieve 3 goals: minimize the selected cell distance to the train station, minimize the distance between selected cells, and maximize the number of cell clusters. After the algorithm has found the most stable solution, we can use the result as the basis for the new urban expansion for Kiryat Shmona. The data that was collected up to this point will be used to further develop the site and determine the character of the construction. Even though the result displays the best cells, there are still variations in the cell quality. We can visualize the cells' grade by coloring them with a gradient and elevating them to represent the difference between the scores. These are the borders of the new urban area, the Superblock. To demonstrate the development of the block, we will focus on one of the created cells clusters. Using a second evolutionary algorithm, we can construct an urban environment inside the block. The algorithm executes a number of program steps to build the environment. At first, 20% of the cluster cells are selected at random to be used as building plots. A footprint of 12.5 by 12.5 meters is placed on top of the selected cells. The footprints are extruded to a height of between 2 to 8 floors according to the cell's core. A network of connections is generated to evaluate the relationship between the buildings. The cells that contain the network are specified as urban area, while the remaining cells are designated for urban agriculture. The ground surfaces are analyzed for sun exposure. Using these rules, we can generate thousands of different urban environments. The algorithm is given a set of goals. Maximize the floor area of the created buildings, maximize the number of buildings, maximize the accumulated score of building cells, maximize the area of urban agricultural cells, maximize agricultural cell sun exposure, minimize the area of urban cells, and minimize the urban cell's sun exposure. I have chosen to use one of the Pareto front solutions for the selected environment. The algorithm produced 50 Pareto front solutions to choose from. In order to select only one solution, I decided to weigh each fitness parameter according to the amount of impact I wanted to have on the final result. To calculate a grade for each environment, the fitness parameters were normalized to values of between 0 and 1, then multiplied by the weights. The parameters were weighed by my personal views as a designer. The multiplication results are summed up for the environment final grade. After reducing the selection of solutions to 4, I chose solution number 9915 as the chosen environment. This solution has a small urban area, a large floor area which can accommodate for more than 9,000 residents, an agricultural area that can allow for the production of close to 100 tons of citrus fruit, grown in urban orchards. The negatives of this solution are a bit high urban sun exposure and the number of buildings is low, only 167 buildings. The generated environment provides us with a schematic representation of the block. At this point, the design process becomes more traditional and manual. The produced block contains circulation network allowing for light motorized vehicles, like bikes and scooters, and for the operation of tractors for the agricultural industry. Spread across the block are urban orchards that are used to grow citrus trees. The spread of orchards in the urban environment allows the block to be productive and preserve some of the original land use. The integration of vegetation in the built environment can assist in lowering air temperatures around the orchards and reduce the urban heat island effect. The urban areas contain public programs such as cafes and restaurants, playgrounds and parks. The buildings are residential and contain mixed-use areas in the ground and lower floors, such as commerce and employment space. This project aimed to provide designers with a methodology for integrating new urban environments within an existing ecological system. Today, the state of Israel is experiencing a dramatic housing shortage that will increase even more in the next 20 years. The state population is expected to double by the year 2050. There are many large-scale projects for new housing neighborhoods at the outskirts of small cities like Kiryat Shmona. In many cases, these neighborhoods ignore the site physical properties and do not sufficiently consider the effects and impacts on the existing ecological system. By using the physical traits of a given site, we can design urban spaces that integrate into an ecological system. Using this methodology, we can still achieve large volumes of residential space with relative low construction and spacious urban public spaces.